Now that we have some background in the design of compression members, let's look at this week's lab assignment. What you're supposed to do is select the members for this truss. Now the goal is to make this truss as light as possible, so you want to pick the smallest diameter possible of circular cross-section steel bars. Another limitation is that you want the diameters to be in even 1/8 inch increments, and we're using A36 steel. Now the detail shows how a joint on this truss is made. So as with all trusses, pinned ends, so your K value when you look at buckling is going to be 1, and you also know that there's no bending in the truss members, they're only tension or compression. So if you remember from statics, your first step here is going to be to find the force in each member, whether it's tension or compression. So you can either work through it using the method of joints, or if you'd like to try software called MD Solids, it does you can install that free for 30 days. And I'll show you really quickly how we would do that. Pick the truss module, and when you select a new truss, you make the spacing. Now horizontally, your truss are 4 feet joint to joint, and vertically 3 feet. The number of spaces that you pick is not really important unless you just want to get the perspective about right. So to create members, you simply drag and drop. And so there's our finished truss. You add supports by clicking next to the joint. So if I click once, that makes it a roller joint. Click on the other direction, that makes that a pin. And on this end, we just have a roller. To put the loads on, I'll just put one of them on. Click right below the joint if you want it to be down, like this one. We'll put 12,000 pounds. And of course, you're going to put the other 12,000 and 8,000 on this. But once you get the truss the way you want it, click Compute, and it'll show the forces, it'll show the reaction forces as well as the force in each member and whether it's tension or compression. So pretty handy tool. Okay. Now, once we know the force in every member, let's talk about how to size them. First of all, if you have a member that's under compression, you have to do an iterative process. So we'll guess at a diameter, and once we have that diameter, we'll calculate the area as well as the radius of gyration. Now remember, the radius of gyration is defined as the square root of the moment of inertia divided by the area. So for a circular cross section, that comes out to be d over 4. So it's not the radius of the circle. The radius of gyration is the diameter divided by 4. And from there, you calculate the slenderness ratio. We've used the symbol lambda here for KL over R. And remember, K, as we said, for a truss member, is always going to be 1. Okay, now you can calculate the stress. It's just P over A. And look at the slenderness ratio. We talked in the last video about the critical value of the slenderness ratio. Well, what you have to decide is whether whether the design you've picked, the diameter you've picked, puts this into short or long column. And so we'll say if we are in a long column, then what you do is simply come up with the design allowable using the factor of safety of 23 over 12 or 1.92. So you calculate the allowable stress directly like that. On the other hand, if it's a short column, you have one additional step, and that is you have to find the factor of safety, which, as we said, varies from 1.67 to 1.92. So if we define R as our slenderness ratio divided by the critical slenderness ratio, there's our equation for the factor of safety, and then here's our equation for the allowable stress. In either case, once we found the allowable stress, we compare our P over A stress to that, and then we iterate. So if our stress is too high, we know we need to make the diameter bigger. But if it's acceptable, then we may want to try a smaller value until we find again that case, the smallest value that meets our requirements, both for the stress and for the fact that the slenderness ratio by code cannot be greater than 200. Now, if a member's under tension, it doesn't matter how long it is. We still have the same equation for stress, and the factor of safety is 5/3 for this, which makes our allowable 21,600 psi. So no iteration is needed here. You can just solve directly for the diameter, but remember to round that up to the nearest 1/8 increment. And so I'll show you 3 examples here. In the first one, we've got a length I've just arbitrarily picked 72 inches. We're putting it under compression, 20,000 pounds. In the second one, we'll look at a length that's half of that. And in the third one, even though we don't need the length, we'll look at a tension member. So here's a spreadsheet that I've set up to analyze the compression members. And so you can see we put in a guess for a diameter, calculate the area, calculate the radius of gyration, and in this case the slenderness ratio becomes 288. So we know that's not going to work right away. I've used some if statements over here to say if things are good or bad, and we can't go over 200. So I know I'm going to have to make this bigger. But also we calculate the KL over R and compare that to the critical value. In this case, it's greater than the critical value, so it's a long column. Now, calculate both the allowables for short and for long column, but then based on the fact that this is long, this is the allowable stress that I'll use to compare to this stress. And of course, the stress is too high, and the slenderness ratio is too high. So let's go up, say, to 1.5 inches. Okay, slenderness ratio is okay now, but our stress is still too high. 1.75. Again, stress is still too high. 2 inches now, everything's okay. Let's see if we can go down 1/8. And no, we can't. So 2 inches is the best design for that particular member. Now, if we move that to 36-inch length, yeah, everything looks okay, but you can see that the stress is very low compared to the allowable. In fact, at 2 inches, we have a short column. If we go down to 1 inch, you can see not quite there. About 1.25. No. 1.5. Everything looks good. 1 3/8 is no good, so we'll stick with 1.5. Okay, for the third example, here's a tension member. And again, from this, you can just simply, we know the allowable stress, calculate the area. From that, find the diameter, and then just manually look at the diameters required, round it up to the nearest 1/8. So when you make your spreadsheets, again, I found that if statements work really well to decide whether it's long or short and which allowable to use. Now, if you get a little more ambitious, you can actually use solver to do this. Now, because of the fact we want this to be in even 1/8 increments, we added another cell here for the diameter in 1/8 increments. This is just an equation that takes that number and divides it by 8. So what I'll do with solver, I have the model set up such that I want to minimize that diameter by changing the number of 1/8 increments, subject to the constraints that we want the KL over R value to be less than 200, we want the stress to be less than the allowable stress, and we want this number to be an integer. And you can see for that first example, we come up with our 2-inch diameter. And 1.5-inch diameter for the shorter column. You can do a similar thing here too with the tension member design, in that instead of looking at this number and rounding it up, you can have the Excel do that for you automatically. I'll let you try to figure out how to do that. So for example, I change this to 25,000. There's my calculated diameter, and I'll take this number and round it up. And so again, these are the solutions if you want to use them to check your spreadsheet. 2 inches for the first case, 1.5 inches for the second, and 1 1/8 inch for the tension member. So now your assignment, you're not writing a full lab report, but you are writing an abstract and turning that in along with your Excel sheet and with your sample calculations. So you want your spreadsheet to be turned in and the results document, which will have the abstract and the supporting calculations. And as it says here, the sample calculation should show the process, and doing it as a flowchart formatting again may help. Is it under tension? Is it under compression? If it's under compression, is it long or is it short? And from your course pack as well, a little bit of instructions about an abstract. Keep it short, 100 to 200 words. You're not going to write a whole report in this case, but in any case, you always want the abstract to essentially be standalone, that you can read the abstract, get the gist of what's in the report, and then decide if you want to go deeper into the report. And make sure you include numerical results as well. You don't have any figures or tables within the abstract. It should be all text. And if you were having other portions of the report, you don't refer to them in the abstract either. And a little bit more about the abstract when you read it. See if you can answer the questions that are shown there. Okay, that's about it.